Hello again, we're right back into it. I said I was going to get to how televisions used to work. And some things still work like this. But I needed to get to the paths that these particles took. All right, so we did all this. You saw electric fields do work, they accelerate charges, and the path it takes is a parabola. Whereas the magnetic field, the path it takes is a circle around the field lines. This is most noticeable for the people who were in astronomy. We talked about this. Magnetic field lines capture particles that go around it in the upper atmosphere, and that's why we see aurora in the northern latitudes. So, but we talked about the work that they did. Here, there is some work because there is we can associate some change in distance with this force, so we can calculate some work. Magnetic fields don't do work. So here's what I'm going to do is I'm going to draw in a possible setup that you can have. All right, my board is going to need some cleaning shortly, but that's okay. So let's just put in a charge. And we're going to give it some velocity. All right, so let's say this is a proton. So Q is plus E. You look that up, that's 1.6 times 10 to the minus 19. There's that. Oh, they're spraying fertilizer or seed or something. That's weird. Okay. That truck came back. And then the mass is going to be about 10 to the minus 27 kilograms. All right, so if you need those numbers, that's what they are. All right, so this is about 10 to the minus 19 coulombs. Very approximate. We're not dealing with, exact things here, because I don't think we're even going to need this. Right? I just want you to have it in front of you. So this charge is going to go into an electric field. And the way we're going to generate the electric field is to have a set of plates with positive charges and negative charges. And this is going to let us pull this charge around. We can flop the order of these, right? Because this could be a circuit. We could take this thing and put in essentially a voltage source. And so we could change the strength of this field. We could put in and alter it. We can make it go the other way if we wanted to. But at the moment, the electric field points downwards. So what this does is it lets us, if we have a screen over here, that is our TV screen. TV screen used to have phosphors on it. An electron hits a phosphor and it glows. And so if you can steer the particle to the particular point, you would cause a particular phosphor to light up, your pixel would light up, and you would show some picture. All right, so we wanted to scan this thing and light it up. And the harder you hit it with, the more energy you transmit into the thing. So you could determine the strength of this basically by hitting it with more particles or hitting it with more energetic particles. And so you could cause brightness changes. Right? So this lets us go up and down. This doesn't let us go side to side on the screen. To go side to side on the screen, we need a magnetic field that will push the charge side to side. So that's what we need. We need our force into the board, and our velocity is that way. I done this right? I've obviously done something wrong. Let me pause for a moment. No, it turns out I was right. What we want is some sort of also moving magnetic field up and down. We'll put up in this case. And so the velocity is that way, and the field is up, and that means it is coming out toward the camera. So the force here would be that way, and the force here would be downwards. So we'll distinguish this. That's the electric force, and this is the magnetic force. And that lets you do this your side-to-side scan. And now the way to generate this would end up being basically a bunch of coils. And that would let you steer a beam around wherever you wanted to on this projected screen, and you could generate your image. And that's well and good. That's not number 4. That's what was getting me wrong, and that's why I paused. But this is how TV used to work. So what I'm going to do is undo this. Take away the magnetic field in this setup. We still have the electric field. And so now what we want is to ask the question, how can we make this charge that is moving at some velocity v go through this thing completely undisturbed? And what we find is that for this charge, the force from the electric field is downwards, so there has to be a corresponding magnetic force upwards. All right, now we do the right-hand rule, and we say the force is upwards, and the velocity is to the right of the board, and so the magnetic field that needs to be in here is into the board. And that's what we mean by a velocity selector. The idea is that we set up an electric field, we set up a magnetic field, and they're crossed. They're at right angles to each other. And when we pass a charge through them at right angles to both of them, right? So say we put v is on the x-axis, the velocity is in the x direction, and so the y direction is going to be our electric field, and the z direction is going to be our magnetic field. If the electric force is greater than the magnetic force, this charge will go down like that in a parabola, roughly. If the magnetic force is greater than the electric force, then it'll go like that, roughly in a circle. If they're exactly equal, then it goes straight through. And then we can write what that means if they're exactly equal. You have QE is QVB, and everything's at right angles, so that sine of phi is going to be sine of 90 is 1. But we can actually include it. All right? And so it doesn't matter what the charge is. The charges cancel out. And so the electric field must look like VB sine phi. So in that WebAssign problem, we had given you the velocity. It was a certain amount. What we had given you was the kinetic energy, right? And I mentioned that a bit earlier. somewhere in the thing, I think. But I do want to mention the idea of the kinetic energy again. All right, so the electron volt was our unit of energy for small atomic particles. And the idea is that 1 electron volt was literally the charge of 1 electron times 1 volt of potential. And so this would end up being 1.6 times 10 to the minus 19 joules. And so the idea is that if you're told what the energy of the particle going through the selector is, you can work out what the velocity has to be. Right? Remember, kinetic energy is 1/2 mv squared. So the idea is that if you're told the strength of the magnetic field and you're told the strength of the electric field, you can work out what velocity you need. Or if you told one of the fields and the velocity, you can get the other field. All right, and you should also be told that these things are at right angles, and then the problem, that's what it does. It tells you that one is along the y-axis and one's along the z-axis, I think. Yeah. So just be aware, this is not a hard problem. I'm going to let y'all work on that for a bit while we go to yet another concept I want y'all to know.